Hello everyone. Can you hear me?
Yeah, I can.
Okay. So how many of you have watched this week's lecture? None of you? Okay, can you see my screen?
Yes.
Okay. Yeah. So in the last week uh, the there was an introduction to neural networks, right? Feed forward neural networks in general, and how training is done um, in a standard feed forward network. So in this week, we'll look into convolutional neural networks. You can all hear me, right? Okay.
Yes.
So, uh, so fine. So, in image data, why do you think CNNs are extensively used and not feed forward neural networks? Anyone? So I'm guessing you all would have heard about convolutional neural networks at some time, right? Why do you think this is used in images but not feed forward networks? Any guess? Okay. So, uh, image. So images is very high dimensional data, right? Like uh, the images which we capture on our phones are of extremely high resolution, and then it is very difficult to actually process the entire image through using a feed forward neural network. So suppose I want to get one feature out of using this entire so if I flatten my entire image and want to use one fully connected layer, so what would the order of that dimension be? Like for example, if you take a very small image, 200 cross 200 is a super minute image actually, and if I have to use one fully connected layer over using this entire input, so that would be extremely huge. Like if I use 40k hidden units, then there will be around 2 billion parameters which we cannot deal with actually. And also that's not the only reason. The other reason is in we would the way we humans process what we see visually is that we look at local regions and try to infer things and get an overall picture hierarchically. So that is why CNNs are used. So what CNNs do is they look at local regions. It's like I apply a filter and I convolve them, move across the entire image, and then look at locally, get extract my features. Then I'll have more filters, and then I keep doing this until I get an global representation of the whole image. So, so what happens here? Unlike feed-forward networks, where all the inputs are connected to all the fully connected layers, neurons in my layers, here my input is local. I mean, at once I am only looking at a local region. So given an input image, I'll use a small filter and move across them. This is just like simple filtering. But then what is the difference between using a regular filter and CNN? Anyone? Like when we predefine those filters, right? Edge detection, we saw Sobel filters, Privet filters, all such things, Gaussian filter to smooth images. So what is the difference between, even there we go look at local regions and then do convolution and get outputs, right? So what is the difference between that and CNNs here?
Yeah, I think people are putting in chat as well, but yeah, so it is a
Okay, I
learned
can't see the
filter.
chat, so if you guys can
Oh,
unmute
okay.
yourself and speak, that would be better.
Sure, sure. Yeah, it is a learned filter, whereas other filters are predefined filters.
Yes, right. So there, it's one particular characteristic we are extracting, right? Like we are either smoothing the image or extracting edges, things like that. Here, we want the network to automatically figure out what is good for it to make the decision finally. So that's the main difference. And yeah, so so the two standard layers which are used in all convolutions are convolution and pooling. Convolution is to do feature extraction, pooling is to reduce my dimensions, right? Like eventually I would want to converge to get one representation for my whole image, so I will put together these pooling layers as well in between to reduce my spatial feature dimension. And at the end, once I am done with all my feature extraction, to make a final decision, like say if I have to do object classification, then I will my end representation, I'll use one fully connected layer. Say I want to do 5 class classification. I'll put 5 neurons and then connect all pixels there. So by the end, I would have reduced my spatial dimension and increased my channel dimensions. Typically, that is how CNNs are used. Mostly I'll have some 256 dimensional vector or something like that, that I'll connect to a fully connected layer to get my classification. So those 5 nodes will correspond to 5 classes, and I learn a classifier. So that is how CNNs are typically used. So what does convolution do? So if this is my filter, basically you just move that around your input and get an output, right? So if this is a 3x3 filter and I'm moving just by 1 pixel, uh, I would get a 4 by 4 output, right? So suppose my image is 10 by 10 and I am using 3x3 filter. What would my output be that time? Anyone?
It is 10 minus 3 plus 1.
Yes. So why is it 10 minus 3 plus 1?
Number of dimensions in the input image minus kernel size plus 1. Actually, it also depends on stride, how much by how much step we are moving the filter.
Right, that is right. So here the stride is 1, so it is just 10 minus 3 plus 1. And now suppose I don't want to reduce my dimension when I'm filtering. I have a 6 by 6 input here and I want to keep it 6 by 6. So what can I do to keep it 6 by 6? The same filter I want to use, but then I want my output to remain the same as my input. Padding. And by what amount should I pad to use a 3x3 filter?
2 by adding by.
Yes. That is right. Yeah. So if my input here is 32 by 32 and also one more thing is say my image is RGB image, then I will have 3 channels, right? One corresponding to R, G and B. So that is 32 by 32 by 3. So whenever we say 5 by 5 filter or 3 by 3 filter, by implicitly we actually mean 3 by 3 cross the depth dimension. So here my depth dimension is 3, so the filter size is 5 cross 5 cross 3, because so it's like I'm moving this 3D volume over the 3D volume of my image, and that will give me just one output at each filter, each location. So what it is actually doing is, I'm moving this 5 cross 5 cross 3 chunk over that entire volume of 32 by 32 by 3, and at each point what I'm doing is sort of dot product W transpose X plus B. So it's like if I flatten that neighborhood from the image and the weight into 1D vectors, and if I take dot product and using a bias, so that's what the output will actually do. So if I do use just one such filter, what the output dimension I get here is 28 by 28 cross 1. But then maybe I would want to extract lots of features, like say I want to detect color information, edge information, shape information, all these things, right? So using just one filter may not give me enough information. So in order to do that, we use multiple such filters. So I have one 5 cross 5 cross 3 filter. So I get this, say I define n such filters, and to get n dimensional, I mean in the channel dimension, I want more feature maps. So suppose I want to get 10 output feature maps here. Here I have one. Instead of one, I want to get 10 of them. Uh, so what are the total number of parameters that would be required for me to get a 28 by 28 cross 10 feature map? So here I have one filter, 5 cross 5 cross 3 is my the number of parameters I have. So if I want a 28 cross 28 cross 10 feature map, so what are the number of parameters I would require?
It will be 5 cross 5 cross 3 multiplied by 10.
So the same operation is repeated but then I would actually initialize all these filters randomly, so each of them can learn different try to extract different features. Suppose if at all I initialize all of them by the same way, then the way they learn will also end up similar. So I can define n number of filters, but then I should always ensure that they are randomly initialized, so that they can start to learn different patterns from the input and not just the same thing. So that's a very important factor. It's not just enough to define lots of filters. So this is how convolution will happen. If I have 6 5 cross 5 cross 5 cross 5 filters and given this input, I would get 28 cross 28 cross 6 output activation maps. So this is like I have a new set of images, each of them corresponding to say some sort of feature. So what happens is in CNN's initial layers of the network learn very low level features, like say one layer will learn to see if there is blue color in some region. Say I want to detect where sky is, so it should learn to activate for blue region, so it will learn just color information. Something else can learn some white, say clouds, then it will look at white regions in the image and it can get activated only for in those regions. So things like that. So basically it's we would have a sequence of, and along with convolution, I mean, so you saw even in feed forward neural networks, we always use non-linearities like ReLU or something, right, in order to learn patterns which can't be learned using simple linear functions. So it's like I have convolution along with followed by a ReLU activation at each output, and so on. So yeah, this is as we discussed earlier. if I need to preserve my output dimension, in such case I pad my input. If I have to use a 3x3 filter, I pad 1 pixel to the left, 1 pixel to the right, 1 to the top and 1 to the bottom to preserve my output, right? So given an input feature map of dimension w1 cross h1 cross d1, and so there are several things here, right? One is what is my filter size, like 3 cross 3 or 5 cross 5, how many filters do I need, by what amount do I want to shift it, should I do zero padding or not. So all these factors contribute to produce an output feature map, right, which is of another dimension w2 cross h2 cross d2. So the weight and height can be calculated this way. So why does this, how does this formula come up? Can someone interpret this for me? Why is this w1 minus f plus 2p by s plus 1?
W1 and H1 are the input image dimensions, and W2 and H2 are the output dimensions, and F stands for filter size, and P is the padding which is provided, and S is stride.
Yeah, so 2p, the p comes up in order to preserve my spatial dimension. Yo. So s comes up because of the stride. Like if I'm shifting by 2x, like skipping 1 pixel at a time, then I am actually reducing my overall dimension by twice, right? So that is why the s comes up, and this is just the output volume is the number of filters I'm using, right? So instead of using fully connected layer, if I'm using convolution layer, so what is the number of parameters I am effective, so to what extent am I reducing the number of parameters? If I had to connect my entire input to say one neuron, then I would have had to use w1 cross h1 uh, so w1 cross h1 into number of filters, that many number of parameters to just get output of one neuron. But then here all I am using is k dimensional filters in spatially, right? So it's an immense reduction in the number of parameters. So here we are sharing my parameters across the entire input, right? It's not global, it's like the parameters are local and which are shared across the input. And why should so one thing is the reduction in number of parameters, but still why should this suppose I have access to lots of compute and I can still learn a feed forward neural network for this input images. In such case, should I prefer using a CNN, or because I have access to enough compute, I'll just train a feed forward network? Why should this structure of CNN actually help learn better things?
I think someone already mentioned, but we can take advantage of locality in space dimension, and also there are things like transition equivariance and scale invariance with the help of max pooling. So those things might help.
Yeah. See, max pooling, all of that is fine, but other than that, one key property of using convolutional networks is to achieve shift invariance. Like suppose in an image, so say this teddy bear is here, and if I slightly shift them to the right corner or left corner, even then I would want to classify it as a teddy bear, right? So in such cases, if I use a feed forward network, how it would look at a teddy bear placed in the left corner and right corner is completely different, because uh, the topmost neurons contribute to something and the bottommost ones contribute to something there. But here, because I'm only trying to look at local regions and still learn some information, even if I shift them, I will still be extracting the same features, right? Like if I shift this teddy bear slightly to the right, I'll extract the same thing, and it will learn to predict what it is. So it achieves shift invariance, which is very much necessary in using image data. Does that make sense?
Yes, yes.
So there are different ways of pooling the network. One is max pooling, which is most commonly used, where we just pick the in each window we just pick the maximum value, activation value, and return it. Average pooling takes the average of all the outputs in that window. Now, let me ask this. So you guys have learned how backpropagation works in feed forward networks, right? In say in this pooling network, um, suppose I want to backpropagate my gradient through this max pooling. So how would you think the gradients will pass? Like what would there's a max pool layer here. I get some gradient, and then I want to pass it back. Because see, there are 4 values. There's only one value I'm picking, right? And I don't care what the 3 other values are. Say this is 10, and the other 3 are 5, 1, 2, or even 3, 4, 5. So whatever it is doesn't matter. All it takes as input from from here on is just 5, right? So how do you think the gradient will be backpropagated here? Anyone wants to?
We propagate whatever we got from upstream just to that specific max pixel, and all other would be zero gradient.
Yes. Yeah, that is right. So I would not pass it through other pixels. I'll only pass it through this. In an average pooling, it again gets not because it's a sum, so uh, equal gradients get passed through to all 4 values in average pooling. So once I have, so typically what happens is whatever high dimensional feature maps I have initially, so I keep doing this sequence of convolution, max pooling, with stride, not stride, max pooling, all of this, and I would have reduced my feature dimension to something like say 5 cross 5 or 7 cross 7 feature map towards the end. At that case, it's a reasonably small spatial dimension, and I would have collected enough channels as output. In such cases, one thing that is usually done is global average pooling. Like say I have 5 cross 5 cross some 256 in final feature map. It can be passed through a global average pooling that will give me a 256 dimensional vector. That is, every channel would be averaged to give me one value. So that acts as my feature representation for my image, which would be a very high dimensional. Say it is some 200 cross 200 cross 3. Now finally that 200 cross 200 cross 3 is compressed to a 256 dimensional feature vector. So that would actually contain the most important information in my whole image that is required to do the tasks from there on. So that vector is, it's either like flattened or global average pooled to get one vector, and then that is passed through further fully connected layers to do classification or things like that. So the first part is to extract features. So once this module is to extract features. To do different tasks, I can formulate these tasks in different ways. Like in the case of object detection, I would need several things, right? See, for classification, say I want to do a 10 class classification, I can simply use one fully connected layer or some 2-3 fully connected layers, and which finally gives me a 10 cross 10 output or something like that. But in a object detection network, so if I want to detect objects in images, what all do I have to detect? Like how can I parameterize my outputs? In classification, so there are 10 classes, means I need 10 outputs which can give me scores for those 10 classes. So it's like a probabilities distribution across those 10 classes, and I'll assign the class with the maximum probability. That's that, no? In an object detection, what are all the outputs I need if I need to detect objects? So it's like, given an image, I need to get a box around an object, right? Like if say I need to detect the face of this thing, so I want a box around this, and also say what object it is. So what are all the outputs needed in such a case? I'll have to predict the bounding box locations, that is where the box actually comes in the image, right? Like it's x, y, w, w and h will define a box. So given an input image, a particular box can be represented by either its center and width and height, or my left corner location and width and height. So I'll have to predict that plus a class. So say I have 10 different types of objects. So my network should actually be able to output several boxes, right? Like there are 5 boxes in the input image, means I should have 5 cross 4 outputs that corresponds to the box dimensions, plus outputs for this classes as well. For each box, what is the prediction for my class? So all this can be formulated using, I can use fully connected layers in different ways in order to get all these outputs. Once I have my feature extraction done, so the rest of this can be formulated in different ways based on the task I have. Yeah, so typically this is how convolutional neural networks work. Given this image, so the early layers extract very low level details, like so you can see there is so these filters act like those simple edge detection filters, or those that detect some shapes or something like that. in the starting, that is how you can see the whole car structure in almost of these filters, right? But then once you go towards the end, in the later stages, you can see activations only in certain regions that are like the car region, something in the middle only, right? So something that says what a car will mean. So the first layers detect very low level features like color and edges or things like that, and then as you go deeper into the network, so these edges get combined. Like say initially my first layer detects a vertical edge and horizontal edge and some cross edge, and my second layer learns to detect a shape like triangle. It will learn to detect things like, oh, if I see three different directions, I mean three different lines uh, meeting each other, this is something like a triangle or something. So it basically tries to learn shapes like circles, triangles, things like that. And then later something else in the few, like in the more deeper in the network, um it will assign like say some, say it's a box or something. In such case it will try to learn that, oh, this means a box, it should have some colors like this. So it will put together information hierarchically to get a global view of the image, and then based on that it will make a prediction. So typically that is how convolutional neural networks work. So any doubts on how fundamentally how CNNs work? No? Okay, so how can we train these CNNs? I'll briefly, these are the slides from the lecture itself, but I'll briefly go over how back propagations happens in CNN. So this is quite different from how it happens in convolutional, I mean feed forward networks, because there all my inputs are connected to all my neurons in the next layer, right? But here my weights are shared across my input. So when I'm applying a filter, some input in my topmost corner does not contribute to an output in the bottommost corner in my next layer, right? So it only contributes to a certain region in my next output. So for simplicity, if we assume I have a single channel input and just a single channel filter which is of size k1 cross k2, so I convolve with this to get an output y which is of dimension m2 cross m1. So this is how convolution happens, right? So here they've assumed I'm placing the filter in the corner, like that is this is superimposed over this corner, just for simplicity, but you can rewrite these equations by even placing it at the center. So what happens is, say in backpropagation, from my output layer I'll have some gradient that comes back here, right? At this stage I have a gradient and I want to compute its gradient with respect to this weight and also with respect to this input, so that I can further pass it backwards. So what is done is, so I need to compute dou L by dou W, that is to update my weights, and dou L by dou X, so that I can pass it back to my previous layers. So these are two things. So I am given with dou L by dou Y here, and I need to compute this and this derivative with respect to these two. So how do we compute gradients with respect to the weights? I need to see which parts of, if I take one particular location of this filter, so W is some k cross k filter, right? And I take one particular location, say the topmost corner, that is A prime B prime. It is one value in the filter. So what all in my output, what all does this weight affect? So in this M2 cross M1 region, if I pick one value in this weight, what all values in this entire region will that affect? Is it just say I pick the first weight here? Does it only affect this particular pixel or the whole all the pixels in Y? Anyone?
All of them?
Yeah, all of them, because to compute the output at every location in every location in Y, I will be looking at a neighborhood and I'll be convolving it with all these filter weights, right? So each weight will be contributing to all pixels. So so each weight will be contributing to all the pixels. So I will use chain rule here, and this loop is because it affects all the pixels. So I compute dou L by dou Y of ij. This is given to me from the next layer. I am getting the gradient, and how W affects Y. So that is the gradient here. This is something I have to compute still. So how is Y actually computed? So this is the definition of convolution, right? X convolved with W, and I need to compute the differential, I mean the derivative of Y with respect to W of A prime B prime. So I can simply substitute it here and then see. So this entire convolution value, the only term that remains when I differentiate with respect to W of A prime B prime is its coefficient, right? Wherever I have A prime B prime, its corresponding X coefficient I'll get. So all I get is if I put A prime B prime here, I'll only get this term. So the derivative of this derivative turns out to be just that value, x of I minus A prime y minus B prime. It's like if it is say the first so if I want to get this value, the corner one, so every time I convolve it here, convolve it with this input, at each location only my topmost corner is what I am multiplying it with, and that will correspond to x of I minus A prime and j minus B prime. So that is what this means. So I can simply putting all these things back in the previous equation. So this is what I get: dou L by dou Y of ij, and dou Y by dou W gives me this. So how does this expression look? It turns out to be again a convolution operation between this gradient. If I treat this gradient dou L by dou Y as a filter and this as an input, so this expression is exactly the convolution operation. So in my forward pass, to go from the input to output, I am doing convolutions, and in back propagation also, to pass my gradients coming from the backward direction and passing it back to the forward direction, what I need to do is still a convolution operation, which is a very nice thing, right? Now so I have found this dou L by dou W. So to update my weight equations, I have an equation like I found dou L by dou W. I can simply do W is equal to W minus eta into dou L by dou W to update my weights, but then I still have to pass it on through this input, through this input and back to the previous layers for further updating of weights. So in such a case, now let us see how do we compute this dou L by dou X.
Ma'am?
Yes.
Can you hear me, ma'am? Ma'am, can you please provide me all the slides today?
What?
all these slides, ma'am. Will you provide me the slides, ma'am?
Yes, yes, we'll put it up. So there's one sheet
Okay.
where we update it, right? We'll put it up there.
Can you please tell me where is it, ma'am?
It's not yet uploaded, but I'll upload it.
Okay. Please, ma'am. Please, ma'am.
Yeah, so there
Thank you.
is one sheet where we are uploading these links, right? There only we'll update it. So these slides are actually the lecture slides itself. It's already available. The ones which I showed, even that we'll put it up now. So now I want to compute dou L by dou X, and let us see. Say I pick this location I prime j prime, and so so this dou L by dou X should be a function of dou L by dou Y, right, through W. So what all pixels does this location affect in my output? Does it affect? So we saw that for every weight value I took, it affects all the values in Y, right, irrespective of its location. So does the same thing apply for dou L by dou X as well? Like, does this location I prime j prime affect the output in Y at all locations? So this is how I am computing Y, right? So by looking at this equation, can you tell what are the Y values a particular X can affect? I mean, X of ij can affect. So this is the location I have picked. In Y, what regions does it affect? See, this filtering is happening locally, right? I will superimpose this weight at this location. That means this is a 3x3 filter, and I am superimposing at I prime j prime. It will only look at this local neighborhood to get an output at I prime j prime in the output in Y, right? So this pixel will only be affecting a few of its neighbors, like in this terminology here. If I take I mean, if I'm superimposing this filter on the corner here, it will only affect these many values. If k1 and k2 is my filter size, right? So starting from here, it will only affect a region of k1 cross k2 and not anything more, because this pixel does not contribute to output at the rightmost corner in Y, right? It does not. If W is a 3x3 filter, at max it will contribute to 3x3 values in Y around that region. Does that make sense? So here, if you see, I want to see what value this topmost pixel is contributing in my output here. So in the first step, when I do this filtering, apply this filtering in the first step, so I'll get an output here. So this pixel is contributing here. When I do filtering here in this region, it will contribute to an output here. That's all, right? Nothing more here. So this the redmost pixel, it will only contribute to two positions here, this and this. Does it contribute to anything more? It doesn't, right? If I shift it one position towards the right, it stops contributing to the output. here also. So this location actually contributes only to a region of k1 cross k2 in my y. So that is the only region I'll consider when I'm taking gradients. So dou L by dou y with respect to that small region P, which is of dimension k1 cross k2, and that with respect to my x. So this term is already given to me, and I need to compute this second term here. So this is again a simple form. So this is how convolution looks like, and I want to compute derivative of this with respect to a particular dou x of ij, and what comes out is just the corresponding weight w of ab. So even in this case, it turns out to be like a simple convolution. Here dou L by dou x at each location is the output of convolution between dou L by dou y in a particular region convolved with w of ab. But then so one difference between this and the previous term is there I had I minus a and j minus b. That is the standard convolution form. Here I have I plus a and plus j plus b. That's like if I flip my filter, or dou L by dou y, if I flip my filter and then do convolution, that's what I get. So this is equivalent to convolving dou L by dou y by with the weight filter flipped. So so the back propagation also turns out to be equivalent to doing a series of convolutions, but it goes from backward direction to forward direction, unlike the forward pass. And one more thing, so in general when we use all these edge filters, Gaussian filters, all of them, their convolution and correlation are the same. That is, whether I have I minus I mean I prime plus a or I prime minus a, it's all the same because those filters are symmetric. But here the filters which are learnt need not be symmetric, like in its extent. If I flip and take a mirror image of the filter, it need not have same weights, because say I want to detect it would have learned to detect some cross edges, like which are like some diagonal edges or something like that. In such cases, if I flip the filter, what I'm getting is something else only. So here flipping gives me a different filter, unlike those traditional filters where flipping is equivalent to, they were symmetric. So here the weights learnt here are not need not be symmetric in convolutions, because they try to learn some patterns, right? So the those weights are actually representative of the templates. It's like template matching of edges or circles. One weight could represent a circle, one tiny circle, and it look for circles only in the image, so something like that, circle or a triangle, upper triangle, different types of triangles, things like that. Yeah, so this is as we discussed earlier, in pooling layers are parameter free, right? We just get, it does not have any weight, but then I still have to back propagate through it. So say if in the forward pass, this is the output of my max pool. In back propagation I will remember, but one thing in pooling layer is, whenever I do forward pass, I need to remember the location at which I have the maximum position. That is, I need to locate, I need to remember that in this feature map I got my max pool output from this location itself, and in this for the second output I got my output from this location. I need to remember all those outputs. So it's like I should have a matrix of with just like pointers to say that this is my so this is where I should get my gradient back, and when I'm doing back propagation I'll pass it through that, and the others will be 0. So that is how backpropagation works in convolution, which is slightly different from how it works in feed forward networks, because all inputs don't contribute to all outputs in CNNs. Any questions on this?
Understood.
Huh?
Everything is clear.
Okay,
Everything
great.
is clear, ma'am.
Okay.
But ma'am,
Yeah.
only one request. Please provide the PPTs for revision and all.
These
Those are very useful.
backpropagation slides are already present in your lecture notes. The other ones we'll upload it.
But ma'am, this is to the point actually.
Huh?
These notes are your PPTs are to the point.
Ma'am, he may not be knowing that the links of the video recordings are also provided. So,
Okay, so in the course site there is one tab where we put a Google Sheet link where we are uploading these live video recordings and corresponding notes which we
Where is
use.
it, ma'am?
It's there in the course website.
Acha, acha. I don't know.
There's one tab where there's a Google Sheet link um, where all these recordings and
Let me
the
see.
corresponding notes which we use in these sessions are available.
Acha. Okay, ma'am.
You can check. So even these I'll upload the notes and video link there.
Okay. Thank you, Puneet.
Okay, I'll in the so this is so you guys have access to have seen those code companions also, right? Like which we show sometimes in these classes and which have references for you to how to use Python notebooks. So I'll briefly go over this in the last 5 minutes. So in the PyTorch library, you can define all these convolution layers and define how many, what is your input dimension, output dimension, kernel size you want, stride you want, which will automatically do your convolution operation. So this conv2d function actually does that. So input number of planes is your input filter size. Like for my first layer, the input filter size, the number of channels is 3, right? 3. And say I want to design 10 filters as outputs. So output number of planes is how many channels I need.
Ma'am, there's some problem with your voice. Microphone, I guess.
Okay. Are you not able to hear me?
No, it's fine.
Okay. Yeah. So these conv layers can be defined using this torch.nn library. So this torch.nn library actually has definitions for all these convolution, fully connected layers, pooling layers, all of them, ReLU, all of them. Like so, this is a basic ResNet block. Uh, so here I'm calling this conv3x3 function, which is defined here, and so normalization layer is again it's a batch normalization layer and followed by ReLU. So I can just define the number of layers I need here in my init block, and then so every time you call this like if I call a basic block, it will by default it will call the forward function in it. So here is where I can actually define so this defines the forward pass. So given my input, I'll first pass through the conv1 block, get an output, pass it through the bn1 output. So in the init block I am actually defining them. Here is where the forward pass happens. So I do a sequence of these operations and give back my final output vector. So several such blocks. These are the basic ResNet blocks, and the entire ResNet model is defined here. Like, so in ResNet, initially I'll have one conf, bn and ReLU layer max pool, followed by these ResNet blocks. Here I am actually defining those four blocks, which calls and prepares those ResNet block 1, block 2, block 3, block 4. And finally I'll have one average pooling layer that will do global average pooling to return my final feature representation, followed by a linear layer to do classification. So when I call the ResNet network, this is what actually happens. It passes to the conv1 batch norm and ReLU max pool, followed by, these are the four main ResNet blocks, layer 1, 2, 3 and 4. Then I do average pooling to get my feature vector, and I flatten it into one single vector and pass it through fully connected layer. This is my classification layer. So so this is the definition of ResNet, the ResNet class. So I call an instance of that ResNet, and so this device actually refers to the GPU ID, which I think is set somewhere in the starting of this notebook. I'm not sure where device is set. Basically, device actually refers to GPU ID. Like I can So I have a model definition. I need an optimizer. So there's several optimizers like SGD, ADAM. All of these are already defined in Torch. I can just call them, and every time I define an optimizer, I need to also give the set of parameters I want to learn. Like, see, sometimes I may not want to learn the entire model parameters, and I only want to learn just a few layers. So in such cases, I only can call that I can only pass those particular layers here. So here when I call model.parameters, it gives me access to the whole parameters in the ResNet model. But sometimes if I need to say learn only the last two layers, then I can pass only the last two layers parameters here. That time every time I call the optimizer, it will only update those two layers.
Ma'am, can we store the value of first layer, like we do a convolution and then we do a max pooling, let's say. Can we store the values for later usage if we want to?
You can so basically, see, this forward function is there, right? When you define this, so every time I call model, like if I say model of image, it actually goes through all these layers and gives me. So suppose I want to do only two layers, right? I can define another function, say define say forward two layers, something like that, and here I'll give x. I only want the output of first two. Say I want the output after this stage. Like you want to do some analysis, like say visualize your feature maps or something, right? In such cases, yeah, you will need to get, and I can use this. So instead of using the default function, I can use model dot. So I can call model dot forward two layers and pass my input. I'll get this output. So based on what you want, you can define new functions in your model block. So forward is the default one. If you don't use anything, it will just call forward. So specific things, if you want to extract, you can always do this.
Okay, thank you.
Forward two layers of my image, I'll pass. Then I'll get my feature maps. So you can use those feature maps to visualize them or do any analysis on that. Something like that. Okay. Yeah, I think we are past time for today. Okay, that is all I had for today. You can try out these Python notebooks on your own, like the demos. And if you have any doubts on particular parts of the function, you can ask me or any of one of us in the next lecture. Like I think you've not really used Torch much until now, right? Like try out these given notebooks. If you have questions on any particular function as to what it does, you're not sure about it, why it is done, functionality of that, you can get back to us in the next session.
Can we use Keras as well?
You can use, definitely you can use. There's nothing wrong. But these notebooks are, I think, used, all of these notebooks are developed using Torch.
Okay.
So, ma'am, which platform is going to be used in today's scenario? PyTorch or Keras or TensorFlow? Which one is going to be used mostly?
Uh, Mostly PyTorch, I think, at least in the research world of PyTorch, because it's more handy and it's more Pythonic. Like it's pretty much like using NumPy, so we all use PyTorch.
Then actually you are not audible. Can you please?
We mostly use PyTorch. PyTorch is very extensively used. Keras also, I think, in some companies they use, but I think in the research world it's mostly PyTorch being extensively used. Okay then, thank you everyone.